So the objective of this work was to investigate whether the origin of the large-scale correlation between morphology and environment of galaxies can be explained from the knowledge of the stellar mass of the galaxies. So basically what we tried to understand was whether, given the prior knowledge of the stellar mass of the galaxies, can this suffice the observed large-scale correlation that exists between morphology and environment of the galaxies. So for doing this work, we need three random variables. We define three random variables. So x, y, and z. So the x characterizes the environment of the galaxies at a particular length scale. Y characterizes the morphology of the galaxies. So basically, y have two values, 0 and 1, 0 for ellipticals and 1 for spirals. And z characterizes the stellar mass of the galaxies. We have divided the galaxies into two stellar mass bins depending on their mass with respect to the median stellar mass. So if the mass of the galaxy is higher than the median stellar mass, it falls in the higher stellar mass bin, and vice versa in the lower stellar mass bin. So z has two values, same as y, 0 and 1. So the methodology of this work, so we have 5 steps. The first 3 steps are: we first constructed a cubic region containing a finite number of galaxies. The galaxies are either spirals or ellipticals. Then we divided the cube into a finite number of voxels. Then we count the number of galaxies in each voxel. The fourth point is that the random variables x, y, and z have respective probability distributions px and py. What does px mean? Pxi is the probability of a galaxy chosen at random settles in the ith voxel, and py is the probability of a galaxy chosen at random is either elliptical or spiral. And additionally, we have pz. What does pz mean? Pz represents the probability of a galaxy chosen at random is massive or less massive. Massive with respect to the median stellar mass bin, the median stellar mass. So theoretical framework, which we have used mutual information. So what does MI mean? The MI between x, which is environment, and y, which is morphology, it computes. So this formula, or what it does is that it computes the reduction in the uncertainty in the outcome of one variable, which is environment or morphology, given the knowledge of the other, and is defined as IXY. So we have two summations because these are discrete variables. So there is a summation. If these were continuous variables, so there would be integration. So what does these two summation imply? So we have x, which goes from 1 to the total number of voxels, and y, which is the morphology of the galaxies. It can take only two values, 1 and 2. This is the conditional probability. So what does this mean? So if IXY is 0, this implies that x is independent of y. IXY can only be positive or 0. It cannot be negative. If it is positive, that means x is correlated with y. Next, we have this conditional mutual information. What does this CMI mean? So the CMI between x, y, and z is the stellar mass, computes the expected value of the mutual information between environment and morphology of the galaxies given the knowledge of the stellar mass of the galaxies. And it's defined as, so here we have 3 variables, so there are 3 summations, x and y. X goes from 1 to the total number of voxel, y goes from 1 to 2, and z also goes from 1 to 2. This is again the conditional probability distribution. Now what does this IXYZ mean? This IXYZ means that if it is 0, it implies that x is independent of y given the knowledge of z. So this means environment is independent of morphology given the knowledge of the stellar mass of the galaxies. However, if ix, y, and z, if it is greater than 0, it implies that z does not contain all the information. So stellar mass of the galaxies does not contain all the information about morphology of the galaxies and environment of the galaxies. This can be positive or 0. It cannot be negative. So now the data. We used SDSS sample for this work. So we used a magnitude and mass limited sample from the SDSS. So our selection criteria was that the outer band absolute magnitude should be less than or equal to -21. We select galaxies lying in the region. This is RA and DEC. Just to remove any patches or holes in the sky, we select this region because this region was clean, and we considered galaxies classified with a vote fraction. So we actually took the sample from the galaxy zoo data. So here we have a vote fraction. So we consider galaxies which have a void fraction greater than 0.8 and the species stellar mass range and its redshift range. So we are probing mainly the low redshift universe. And then we wanted to juxtapose our observed results with the Millennium samples. So we obtained data from three semi-analytical models implemented on the Millennium simulations with exactly similar selection criteria as that of the SDSS. So this is the histogram which shows the number of galaxies as a function of stellar mass. Then the results. So the physical significance. So we have this SDSS original profile, and we have this SDSS Poisson and randomized profile. What does this mean? Is that this original profile, the MI for the original profile is greater than the Poisson data. This means that there is a mutual information between morphology and environment, and it exists up to 90. This is actually 87 megaparsec. So it extends up to 87 megaparsec. But these Poisson data sets, it is not zero. It has some positive value. This is because we are working with a finite sample, and so there is some fluctuations, and because of those fluctuations, we are seeing a positive MI. But this is less than the original data. Now we wanted to compare SDSS with semi-analytical models. So we have the three models here in SDSS. We find that on small length scales there is a so on small length scales there is no disagreement. Whereas on the other, when we go to a higher distance beyond 20 megaparsec, we see that there is a discrepancy between semi-analytical models and observations, where the semi-analytical models does not seem to predict the existence of a large-scale correlation between morphology and environment, whereas observations predict, observations show that there is a correlation between morphology and environment, and it exists up to 90 megaparsec in our sample. Now, to understand the CMI, what does CMI mean? The CMI for the original data can be greater than or equal to the MI for the Poisson data. Now, there are two possibilities. If it is equal or if it is greater than MI. If it is equal to MI, this means that this implies that stellar mass can explain the large-scale correlation between morphology and environment. However, if CMI is greater than MI, this implies that stellar mass cannot explain this large-scale correlation. From this plot, it is clear that CMI is greater than MI. So this profile you're seeing, this is the IXY for the SDSS randomized. So this is the MI for the randomized data. We see that the CMI is greater than the randomized data. So this plot clearly explains that the stellar mass of the galaxies cannot explain the origin of the large-scale correlation between morphology and environment. This is the take-home message. Now we find that there's a discrepancy between SDSS and semi-analytical models, similar to the previous ones, mostly on the large length scales. Conclusion. So we have only two results in this work. The first result is that the physical origin of the large-scale correlation between morphology and environment cannot be explained from the knowledge of the stellar mass of the galaxies. So the stellar mass of the galaxies is often presumed to be the most fundamental property of a galaxy, and it is the most fundamental property of a galaxy, but it does not contain all the information about other galactic properties. And the second result is that semi-analytical models do not agree with observations SDSS at larger length scales, which from this work we found that greater than 20 megaparsec, there is a discrepancy between semi-analytical models and observations. Thank you.
Thank you very much for interesting talk. We have 4 minutes for question Q&A. So we check Slack. Okay, so we have many questions here. First one is from Daniel Santos. Very interesting talk. I am curious about the methodology of your work. It seems that your methodology is focused on looking the probability of three defined variables being related together. Please correct me if I'm wrong. Previous studies have studied morphology, environment, stellar mass by using continuous discrete measurements of three variables. For example, plotting fraction of spiral galaxies versus galaxy density. Is there any scientific motivation why you use your current methodology, Like, does it give a certain advantage compared to other studies method, or maybe a different way of looking at this morphology environment stellar mass problem?
Okay, yeah. So this is a good question. So to answer this question, I would this framework it can the things that this framework can trace both the linear and non-linear correlation between morphology and environment. It can track any kind of correlation, and it is very sensitive to all kind of dependency. It can track any kind of correlation between morphology and environment, not specifically linear. And density, yes, we have used density. So density is defined in the variable x. X is the environment. So it actually what it does is that it calculates the number of galaxies in a voxel, and then it calculates the number of galaxies which are spiral or elliptical. So it actually contains the information about the galaxies, about the density of the galaxies, and as well as the morphology of the galaxies. The and the reason why we have used this framework is that from the CMI plot, we can clearly see that uh, the x, y, and z, if it is zero or if it is greater or if it is equal to the mi of the Poisson data, it can simply we can simply say that the stellar mass can explain all the information about of the morphology of the galaxy. So I mean the framework is simple, and it is computationally inexpensive, and it is robust enough to trace any kind of correlation between morphology and environment or any kind of galactic properties as a function of environment. So this is why we have used this framework. And to answer the second question, why model fails at large distance? So the semiotical models it fails at large distance because uh, I have I have read in a paper in which they said that in semiotical models the real radius is often assumed to be the spatial extent up to which morphology or up to which environment is predicted to influence galaxy properties. So if those kind of prescriptions are used in semiotical models, this can lead to discrepancy between observations and semiotical models. So such kind of prescriptions need to be avoided. We do not know for sure what causes this discrepancy. So this is purely a guess. So this could be one of the reason why we are seeing a discrepancy between observations and semiotical models.
Okay, thank you very much. Let's
Thank
move
you.
on to this question. This is from Tomogoto. Why does model fails at large distance?
He finished. He explained. Let's put here.
Oh, okay, okay. Sorry. So, is there any questions from local people? Um, we still have 2 minutes. I have a small question.
Yes.
Um, so you show the mutual information as a function commutative distance. That indicator always decrease toward a higher distance. Why this depends on distance?
Uh, I'm sorry, I didn't get your question.
So you showed mutual information as a function commuting distance.
Yes, yes.
So that value is always decreased towards distant universe, toward uh, longer distance.
Yes.
That information always decrease.
Uh, because a galaxy which is near to one galaxy will contain more information about a galaxy. As we increase the distance, the information shared between one galaxy with the distant galaxy will decrease. This is how to explain it. This is very difficult to explain. I mean, so if two things are very close to each other, they will share more information with each other. As you increase the distance between the two objects or two galaxies, they will share lesser and lesser information with each other.
Okay, I got that point.
Yes, yes,
Thank you very much. I have one more small question.
yes, yes. Please, please.
When you talk about the morphology, so how did you
Yeah.
parameterize this morphology?
Yeah, so we used actually a Galaxy Zoo data. So here the volunteers have visually classified the galaxies as repticals or spirals. So that is why we have used so and there is a vote fraction. So what fraction of the volunteers has voted for this galaxy as a spiral, or this galaxy as elliptical. So we have used zero point 0.8 as the cutoff. So if a galaxy is being classified as a spiral with a vote fraction greater than zero point 0.8, we call that galaxy a spiral. And if it is elliptical, same for elliptical. So the zero point 0.8 we have used as a base to actually select the samples which have there are some galaxies which have been classified as spiral with a vote fraction of zero point 0.6 or zero point 0.7. So this seems spurious. So we have not taken those galaxies into our sample.
Okay, okay, thank you very much. I understand. Okay,
Thank you.
so let's thank the speaker again. So let's move on to the next speaker. Next speaker is Mr. Oliver